I'm the mad Mr. Daycock, and today I'm going to be teaching you how to use the Moivre's theorem to prove trigonometric identities. So, here are two trigonometric identities, the double angle formulae for sine and cosine, and we're going to use the Moivre's theorem to prove them. You should recognise these, they are fairly standard. If you don't, make sure you go over your angle addition formulae and double angle formulae again to make sure you know that these things are things that are quite important. Okay, so the way we're going to do this, we have to ask ourselves what power of de Moivre's theorem we're going to use. And the answer is, because this is a 2 here, 2 theta, we're going to use a power of 2. So we're going to get cosine theta plus I sine theta squared. And using de Moivre's theorem, that tells us that that is cosine of 2 theta plus I sine of 2 theta. And here are the 2 thetas appearing already. That's good. Second step, we're just going to expand this out. And we're going to get cosine theta squared plus 2 lots of cosine theta times by I sine theta. Notice that the second term in the brackets is I sine theta, not just sine theta, plus 1 lot of I sine theta squared. And that's just the left hand side. The right hand side is still exactly the same. So that's going to be identical to cosine of 2 theta plus I sine of 2 theta. And remember, the identical to sign means that it's true for all values of theta. Now let's expand out this left hand side, make it a little bit nicer. We're going to end up with cosine squared theta plus 2I cosine theta sine theta. And then I squared is -1. And so when we're squaring this, we're going to get minus sine squared theta. And that's still cosine of 2 theta plus I sine of 2 theta. Okay, and now all we want to do is gather terms. We want to gather the real part and the imaginary part. And this is fine because if theta is real, then cosine and sine are all real as well. And so the only complex part is the fact that we've got an I in there. So we get I write it as cosine squared theta minus sine squared theta plus, and I'm going to write the I out front, plus I lots of 2 cosine theta sine theta. And that is still identical to exactly what was on the right hand side at all. We have not at any point changed the right hand side. And now it's just a matter of equating real and imaginary parts. So our real part here is cosine squared theta minus sine squared theta, and our real part over here is cosine 2 theta. And so we get from real parts cosine 2 theta is equivalent to cosine squared theta minus sine squared theta, just as we wanted. And then we want to equate our imaginary parts. That's the bits that are being multiplied by I. And we get exactly the same way. Sine of 2 theta is equivalent to 2 cosine theta sine theta. And that's just from our de Moivre's theorem, and it's proved our double angle formulas in a very nice, easy way using de Moivre's theorem. There we go. Okay. Let's go on to a slightly more complicated example. Here we want to use de Moivre's theorem to prove that cosine of 4 theta is identical to cosine to the 4 theta minus 6 cosine squared sine squared plus sine to the 4 theta. And again, we're going to look over here and go, we're looking for 4 theta. So the power of de Moivre's theorem we want to use is to the power of 4. And we get cosine of theta plus I sine theta to the power of 4 is identical to cosine of 4 theta plus I sine of 4 theta. and then expand again. In this case, we want to use our binomial theorem. You want to either use Pascal's triangle or your calculator to get the coefficients. We'll just use our binomial theorem, and we'll get cosine theta to the power of 4 plus 4 being our binomial coefficient, cosine theta cubed multiplied by I sine theta, plus our next binomial coefficient is 6. 6 lots of cosine theta squared sine theta squared, except remember our sine theta always has an I on it, plus 4 lots of cosine theta, so I sine theta, cubed plus I sine theta to the power of 4. And that there is just the left hand side, so that is still all equivalent to cosine of 4 theta plus I sine of 4 theta. Now, let's expand all that out, make it a little bit neater to look at, and we're going to end up with cosine to the power of 4 theta plus 4i cosine cubed theta sine theta plus 6 lots of I squared cosine squared theta sine squared theta plus 4 lots of I cubed cosine theta sine cubed theta plus I to the power of 4 sine theta. And as always, that is still equivalent to cosine 4 theta plus I sine of 4 theta. And now we need to deal with these I terms. I is just I squared is minus 1, I to the cubed is minus I, and I to the 4 is just 1. And that's an important rule. You might want to write that down. You have I is, of course, I to the power of 1 is I squared equals negative 1, I cubed equals negative I, and I to the 4 equals positive 1. And it just cycles from there. It will go I, minus 1, minus I, 1, I, etc. forever, through as you're increasing powers and decreasing ones. If you do I to the 0, you get 1, unsurprisingly. But if you get I to the negative 1, you get minus I. Okay. But carrying on from there, now let's input that information and see what happens. Well, we're going to get cosine 4 theta plus 4i, because I is just I, nothing's changed there. Cosine cubed theta sine theta. Now, I squared is minus 1, so this has changed. We get just minus 6 cosine squared theta sine squared theta. And at this point, you might be going, oh, I see where it's going. Maybe. Minus 4 lots, because we've got a minus now, of I cosine theta sine cubed theta. And then I to the power of 4 is just 1, so plus sine to the power of 4 theta. And as before, as I've said every time, that's just equivalent to cosine 4 theta plus I sine of 4 theta. And then we just need to finish it off. And all we have to do to finish it off is collect the real parts and the imaginary parts. So the real parts are cosine 4 to the power of 4 theta minus cosine squared, sine squared, and the plus sine to the 4. So we're going to have cosine to the 4 theta minus 6 cosine squared theta sine squared theta plus sine to the sine to the power of 4. Okay, and then plus I, because we now want the imaginary part, and the imaginary parts are this and this. We've factored out the I, so we're left with 4 cosine cubed theta sine theta minus 4 cosine theta sine cubed theta. And that is identical to exactly what's been on the right hand side every time, cosine 4 theta plus I sine of 4 theta. And now we can finish the question by equating the real parts. We get that cosine of 4 theta is identical to cosine to the power of 4 theta minus 6 cosine squared theta sine squared theta plus sine to the power of 4 theta as required. And we have answered the question. At this point you can stop and be done, but I'm going to go a little bit further because I want to show you some nice little bits here that allow us to rewrite it and also spot another thing. So first of all, this is actually a buy one get one free situation. Sure, we've equated the real parts and got a formula for cosine of 4 theta, but if we equate the imaginary parts, we'll still get a formula for sine of 4 theta. We weren't asked to in this question, but it's still something that we can get, and it's always worth having a look at things like this. So we get 4 cosine cubed sine theta minus 4 cosine theta sine cubed theta. And there you go. That's our equating our imaginary parts gets us a formula for sine of 4 theta as well. So that's nice. Now, there's one little step we can go further, and it works with the cosine, but it won't with the sine in this case. But with the cosine, what we can do is we can use the fact that sine squared theta plus cosine squared theta is always 1 to tell us that sine squared theta is always 1 minus cosine squared theta. And therefore, if I square both sides, sine to the 4 theta, because I'm squaring it, is equal to 1 minus cosine squared theta squared. And now I can substitute those in for the sine squared here and the sine to the 4 here. And I get an entirely different formula for cosine 4 theta. Cosine to the power of 4 theta minus 6 cosine squared theta multiplied by 1 minus cosine squared theta plus 1 minus cosine squared theta squared. And then I just need to expand these brackets. Cosine of 4 theta is going to be cosine to the power of 4 theta. If I do this in green, minus 6 cosine squared theta times 1 is 6 cosine squared theta. And then 6 cosine squared theta multiplied by cosine squared theta. And then negative times a negative, it gives us a positive. We get 6 cosine to the power of 4 theta. And then adding on the end, we get plus 1 minus 2, because notice we have to expand this bracket, cosine 2 squared theta plus cosine to the power of 4 theta. And then collecting like terms, cosine 4 theta is identical to, first of all, we've got this, this, and this term all to the power of 4. So we get 8 cosine to the power of 4 theta. And then we have this term and this term, which are both to the power of, both squared, both power of 2. We get minus 8 cosine squared theta. And lastly, we've got a 1 on the end, so we get plus 1. And there we go. That there is another formula we can use for cosine to the 4 theta. And what's really nice about this one is that it's entirely in terms of powers of cosine. There's no sines involved whatsoever, which makes it really, really nice formula if all you have is cosine, or just you've got, well, someone tells you that cosine theta is equal to 0.5, you can immediately get what cosine of 4 theta is just by plugging 0.5 in for cosine theta, and so on and so forth. Okay, In the next video, I'm going to be showing you sort of in reverse how to get powers of cosine or sine in terms of double angles and quadruple angles, etc. And I'll see you in the next video for that. Thank you very much for watching.